to introduce a little bit of the lesson for next time that you're going to read about this weekend, okay? Because honestly, the next two lessons take more time than these last two have, okay? So section 2.6 is on continuity of functions. What it means to be continuous. Okay? And so I'm going to share with you guys some notes I sometimes give on this, and we'll go from there. So, the definition of continuous, can you write it down? A little quiz. Well, it's in the back on this board actually if you need it. But I want to just point out that when I write that equation, limit as x approaches, here, I'm using C here instead of A, so I'll do that. When I say limit as x approaches C of f of x equals f of C, this is what it means for f of x is continuous at x equals C. So basically, maybe I should have started with this box. F of x is continuous at x equals C means, there it is. Limit as x approaches C of f of x equals f of C. But I guess what I'm saying is that's three statements in one. And your book does it this way. They say, hey, you have a checklist of things to check if you want to see if something's continuous. You need three things to happen. You need f of C to be defined. Hey guys, on the group work number 3, it's on the back board or it's on your sheet, we had this function. We had f of x equals x squared minus 25 over x minus 5. I'm going to tell you this is not continuous at x equals 5. I mean, we have the limit. The limit ended up being 10, but we don't have f of 5. F of 5 doesn't equal 10. So you need a couple things to happen. You need f of c to be defined. You need the limit to exist. And you need them to be equal. Okay? You need them to be equal. And the reason I point that out is because you can imagine someone does this. Here's a problem. We could say, hey, f of x equals, and this is what's called a piecewise defined function. I could say x squared minus 25 over x minus 5 if x does not equal 5. But then what I'll do is I'll say if x equals 5, I'll make it equal to something. I'll make it equal to 0, let's say. This guy is also not continuous at x equals 5. Why is it not continuous at x equals 5? Well, because if you drew the graph, let me show you what it would look like. You'd still have that hole. Where did I say that hole was? Yeah, 5 comma 10. So the limit exists. It's true that the limit as x approaches 5 of f of x is 10. We have that. But they also defined f of 5 to be 0. That's way down here. So when I look at my checklist of three properties, I have f of c defined, I have the limit to exist, but they also have to be equal. If you don't have that, you're out of luck. What would I have to do if I want to make this a continuous function? Here, let me get my red pen out and fix it. You don't want to make this 0. What do you want to make it? How about 10? If I make it equal 10, this dot isn't there anymore. Where's the dot? Right here. I would like color it in. Then it would be continuous at that point. Is this okay? So these are some ideas. Now, in your book, there's a bunch of theorems about continuity. They're going to tell you that lots of functions that you are very familiar with are continuous. Polynomials, they're continuous everywhere. The trig functions are continuous everywhere except for, like, if there's an asymptote. We saw some asymptotes. But they're continuous everywhere else. Okay? Sums of continuous functions are continuous. And all this has to do with the idea of limits. Because limits are in the definition of continuity. So next week we got to get you the precise definition of limit, and then we can actually take a look at the proofs of some of these things. You guys have a great weekend.
Okay, I'm going to give you guys a little bit of help here. So number one, f of x. If I want to sketch a graph of what that looks like, right? So you could pick any positive number you want. Say I put in a 3. What's my output then? Yeah, 3 comma 1, because you get 3 over 3. Or what happens if you put in a 2? Okay, or a 1, you get 1, right? So is that true? Yeah. What happens if you put it, can you get any other outputs besides 1? I guess that's the question. You can get negative 1, right? So if you put in negative 3 as an output, you get negative 3 over positive 3, which gives me negative 1, right? So if I were to graph all of the outputs, of course there is no output at 0, but you'd have a line here right along y equals negative 1, and you'd have a circle here and then a line here right across, well, y equals 1. Right? That's the graph of f of x. Okay? And this is different than h of x. This is what you might call a jump discontinuity at x equals 0, right? When x equals 0, it's undefined. Whereas h of x, what's the graph of that look like? Well, remember that we've been finding a limit, right? We know that this one, h of x, is not continuous when x equals negative 1. We know that, right? And yet, you could still find the following. If you want to find the limit as x approaches negative 1 of h of x, how do you do it? Well, we've been factoring the numerator, factoring the denominator is just x plus 1, and so we cancel, right? And so what you end up doing is computing the limit as x approaches negative 1 of just x minus 1. And so what do you get? Negative 2. Right? So remember, when we say continuous, we have a little idea on the board. We want the limit as you approach a to be the same as h of a here. Okay? Here my a is negative 1. We have the limit exists. Okay? Well, the picture of this graph, the graph basically looks like the line y equals x minus 1. So now what's that look like? Well, it goes through, for example, 0, -1, and it has a slope of 1. So it goes like this, and the only place it's not defined is right here at that hole, and that hole is -1 comma what? -2. That's what we just computed. It's the limit that exists. Are you guys with me? Okay? And so, the reason that this is called a removable discontinuity is that you can define the function in a different way and make it continuous. Let me show you what I mean by that. Here, I'm going to make a new function. I'm going to call it capital H of x. And I'm going to define it using some different cases here. Does this make sense to you guys? So how's this work? Well, what you do is you say, look, we're going to let this function be x squared minus 1 over x plus 1 if x does not equal -1, just like we did before. And we're going to say that if x equals -1, what do we want the output to be? -2. And what I'm going to say is capital H of x is continuous everywhere. Right? It would have the exact same graph as little h of x. What would be the only difference? You kind of color in the hole. So you have a line. Does that make sense to you guys? Okay. So this is why we call it removable, is because you can just define one point differently and you got it. That's called a removable discontinuity. I can't do that here. I can't do that here. One other thing I want to point out. Last class, we tackled what I think is the most difficult material in the entire book. That's Calc 1, Calc 2, and Calc 3. Understanding the definition of limit using epsilon and delta, right? I mean, they're both involved. We did the one with the infinite limit with the capital N. I think that helped a little bit, actually. But anyways, when I say that this limit is -2, that means for any epsilon greater than 0, give me an epsilon neighborhood, you'll be able to find a delta neighborhood around that hole so that all the outputs end up in the epsilon neighborhood. Okay? The reason that this limit doesn't exist, well, what we used to say is, look, the left side and the right side aren't coming together. But if you think about it from an epsilon point of view, let's make epsilon equal to 1. Okay? Suppose somebody says, hey, I can remove this limit. I'll color in this hole. That's going to be my limit. Maybe as I'm coming in, I think the limit is 1. Well, you make an epsilon equal to 1, it would be a neighborhood like that. And you say, what should delta be? Well, the problem is that delta is going to be a neighborhood around 0. And I don't care how small you make delta. If you're on the left side of 0, what's the output? -1. It's not going to be in the epsilon window. The point is that if you're on the left side of 0, we are far apart from where we are if we're on the right side of 0. We're not approaching a single point like we are here. And that's what that epsilon argument is trying to capture. So I thought I would point that out. Now I want to give you a chance to do number 2. You'll notice I had to handwrite in a little equal to here so you'd know kind of what to do when x equals 0. This is another function by cases. But before you go back and talk about that one, there's a nice example I often give that I want to go ahead and show you. And it's, well, give me 1 second here. I'm going to punch it up. It's on the PowerPoint that I have on continuity and one-sided limits. Right here. You see, we know lots of functions that are continuous. But I guess what happens is when we start mixing together compositions of functions, that's where maybe you can get a little bit worried about, hey, is this function continuous or not? Okay, here's the example. Show that this function is continuous on the whole real line. Okay? So there are some nice facts that I'm going to use if I want to show this. Okay? And these are facts from your book. Your book calls these, and they were in a previous section, I guess, but your book calls these the limit laws. I'm trying to remember the exact section they were in. I think, shoot, I'm losing it. Let me punch this up for a second. The limit laws. They say things like this. If you have the limit as x approaches a of two functions that are added together, okay, that equals, well, what do you wish it equaled? Tell me. If you were writing the math book, what would you hope that this actually equals? Wouldn't you hope you can kind of distribute the limit of the first function plus the limit of the second function? It'd be nice if that were true. And it turns out it is. A fancy way to say it, I guess, or maybe a way with English to word this, would be the following. I can say the limit of the sum is equal to, what would I say? The sum of the limits. Okay? You could prove that this is true with the epsilon delta stuff. I don't want to do that right now. I just want to kind of alert you to the fact that this is going to be true. It's also true that the limit of the fill in the blank is equal to the fill in the blank of the limits. Can you give me another word kind of like sum that you learned over the years in your algebra class?
Difference.
There's one. Difference. Which means, of course, we subtract. Do you think that's true? You're right. The limit of the difference is the difference of the limits. Another word. Product. The limit of the product is equal to the product of the limits. True. Okay? And there's all these theorems listed in your book, and I got to the point where I said, I'm not going to list them all for students. I'm going to tell you that it's almost true that you could just fill in the blank. Limit of the blank is the blank of the limits. That's almost completely true. As a matter of fact, for this problem that I'm trying to do right now, show that this is continuous on the whole real line. It would be really cool if the limit of something raised to the 2/3 power is equal to something raised to the 2/3 power, that limit can go inside. The limit of the power is the power of the limits. And guess what? It's true. They can prove that too. What else would I need? Well, I have a big fraction. So I need it to be true that the limit of the, what's the word that goes in there where that blank is? Kind of like sum, but when you divide. The limit of the quotient is equal to the quotient of the limits. That's almost true. That's true as long as you don't make the denominator what? 0. So you do have to check that you don't make the denominator 0. Okay? Well, because you have all these limit laws, it turns out that continuous functions, once you have kind of your basic continuous functions, you can create new ones by putting them together in lots of ways. So, for example, we know polynomials are continuous on the whole real line. Well, let me just write it this way. On negative infinity to positive infinity. Right? And let's write down that function again here that we're thinking about. We're thinking about f of x equals x minus 2 over x squared plus 4x plus 5 to the 2/3 power. Okay? Now, let me continue my argument. We know that polynomials are continuous on negative infinity to positive infinity. So what that means is, if I take the function, I'll call it y1 equals x minus 2, and y2 equals x squared plus 4x plus 5, these guys are both continuous on, well, negative infinity to positive infinity, right? Because they're polynomials. Right? Next. So I use this fact. And then I say quotients of continuous functions are continuous, and then I'll put in parentheses, unless they make what happen? The denominator, what am I going to say? 0. Okay. Quotients of continuous functions are continuous unless they make the denominator 0. And what am I going to say about this problem? What would make the denominator 0? Well, I guess we could solve that, right? What would we do? How do you solve that? So, let's see. X squared plus 4x plus 5. We want to make sure that, the question is, where does that happen, right? Where does x squared plus 4x plus 5 equal 0? What would you guys say? Why don't you talk about that for a minute? I'm going to pause this, and you talk to the people in your group about that for 1 minute and see if we can kind of finish this. But let's understand why the calculator said there's no real solutions, right? What did it do? You guys were using the quadratic formula, which is x equals, help me out. Negative b plus or minus square root of b squared minus 4ac all over 2a. All right, beautiful. Now, when you said no real solutions, that means what kind of solutions did you get? Imaginary, or we call them complex numbers, right? And you're going to get imaginary numbers if what happens? If this thing is negative. Now let me check this out. In our problem, A equals 1, B equals 4, C equals 5. Am I correct? So if I do 4 squared minus 4 times 1 times 5, I agree. You're taking the square root of negative 4, you're going to get imaginary numbers. So the answer is, where does this equal 0? The answer is nowhere. That should probably be one word, right? Nowhere? Nowhere. No. Anyways, that's doesn't happen anywhere. And so now what can I say about that big fraction? X minus 2 over x squared plus 4x plus 5 is continuous, yes, on the whole real line. That's right. It's continuous on the whole real line. And so now the last thing to do is to think about what happens when I raise it to the 2/3 power. Well, if you have a continuous function and you raise it to a power, you get a continuous function as long as it's defined. And by the way, when you have a fraction exponent, I know 2 means power. Do you know what the divided by 3 really means you're doing? You're taking a cube root. Now, square roots, we have a problem. We have to keep everything positive. But cube roots, take the cube root of anything. Okay? So we will conclude that x minus 2 over x squared plus 4x plus 5 to the 2/3 is also continuous on negative infinity to positive infinity. Okay? So again, all these rules that they talk about in this section about all the things you can do, you can put continuous functions together and get new functions that will also be continuous. It works pretty nicely. But it all comes down to the fact that limits behave very nicely. Matter of fact, this little law that I put up here, the limit of the blank is equal to the blank of the limits. I don't think you'll get something that you can put in the blank that doesn't work until Calc 2. It turns out in Calc 2, the limit of the limit doesn't always equal the limit of the limits. What I'm saying is this: if you have 2 limits and you try to switch the order, sometimes you get in big trouble. But we're not doing anything with 2 limits at this point. Okay? And I don't know if you'll actually get it. Depends on your Calc 2 teacher. But it comes up eventually. So for us, let's just say the limit of the blank is the blank of the limits, and we're in good shape. And so now I'm ready to talk about that group work problem. Yeah, group work. It's more like Paul work. I'll do it in front of you. All right, here we go. Number 2. Find any real numbers for which the function is not continuous. First of all, x squared. I know what that graph looks like. And it's for x bigger than or equal to 0. I had a typo, so I filled it in. And so, of course, we know that for anything bigger than or equal to 0, I have this parabola, and we are continuous. Okay? Now, I'll be honest with you. That other thing right there, 1 minus cosine x over x, I don't know what it looks like. And I didn't graph it yet. But I still know that when x is less than 0, we are continuous. How do I know this? Well, because I know something about cosine. That's right. Okay, so fact, the trig functions, this was in your reading for today, are continuous on their domains. And what we're going to be doing on Friday, it's going to be very important that the functions are continuous. Okay? It's kind of like if we get a function that's not continuous, we're out of luck. Okay? We're going to have continuous functions. So that's why the book actually proves that sine and cosine are continuous. Hey, by the way, once you know sine and cosine are continuous, how do we get that tangent is continuous?
Just the quotient.
It's a quotient. And a quotient of two continuous functions is continuous, except for the places where what happens?
0.
So what would we have to worry about? What's in the denominator of the tangent function? So anywhere the cosine of x equals 0, we're going to get an asymptote. But everywhere else, it's going to be continuous. And if you know what the tangent function looks like, you'll say, yeah, I know that. The tangent function, you get these little waves. Well, I drew it backwards, but try that again. Come on, Paul. You used to teach trig. There we go. Okay? So they look kind of like that. And they're continuous. Anyways, what's my point here? Let me kind of go through how I know that this side, whatever it does, I don't know what it does, but it's going to be continuous. Why? Well, the trig functions are continuous, right? So 1 minus cosine x, is that continuous? Sure. I subtracted two continuous functions. I divide by x, is that continuous? It is, as long as x does not equal 0. So I know we're continuous over here, and I know we're continuous over here. And actually, I guess there is only one point that I'm worried about not being continuous at. And which point is it? 0. Because I don't know when these two match up, am I going to hit the same point from the red as I am from the blue? That's the issue here. You guys with me? All right. So let's see if we can compute it. Well, the question is it true that the limit as x approaches 0 of this function, 1 minus cosine x over x, equals, what do I really want it to equal?
X squared.
Well, I want it to equal the same thing as x squared as x approaches 0. What's the limit as x approaches 0 of x squared?
0.
We know that hits at 0. And the question is it true that this limit is 0? That's the question. And if it is, then this function would be completely what? Continuous. Well, remember I said first thing you do is try plugging in, right? What's the cosine of 0?
1.
Cosine of 0 is 1. So what do I get when I plug in 0 into this function? 0 over 0. What does that mean? Indeterminate. Maybe we can compute the limit. Now, it turns out you can, but it takes more work. And you need the squeeze theorem, which is something we studied, and I just don't have time to do it on this worksheet, okay? We'll see at the end if we do it today, Friday, or Monday, or when. It's coming. It's coming. But I'll give you the answer. The answer is yes, this limit is true. Okay. I just haven't said why yet. Why? Later. Okay. Enough of that. Last problem, problem 3. Show there is a number x between 0 and pi over 2 such that x is the same as cosine of x. Does this problem seem kind of random? Well, it might. If you read, there's other examples like this. We're going to use a theorem from the reading. This is an application of, does everyone remember the name of the theorem that seemed kind of big in this section? IVT. Sometimes they just call it IVT. Okay, I'll give it to you. Intermediate value theorem. The intermediate value theorem. And let me show you how I do this. Okay. Oh, what's the theorem say? I should give it to you. So let's do that. Let's give you some notes. Here we go. The intermediate value theorem. By the way, this is a theorem that actually has a name. Sometimes they'll say theorem 2.2. If they say that, not so important. But if it has a name, you can guarantee it's important. All right? This is a big one. What's the only other theorem you guys know that has a name?
Squeeze.
Is the squeeze a theorem? I guess it is, right? Actually, you're supposed to prove it for homework. 54. Wasn't that problem 54? Didn't you guys do that? Show that, basically prove the squeeze theorem. Or you tried. I'll go over that. Okay, so there's one. Any others you know? Pythagorean theorem. Okay. Well, here's a big one. Intermediate value theorem. Of course, a theorem is something that you can do what? You can prove. Unfortunately, we are in no position right now to prove the intermediate value theorem. They don't even include the proof in the appendix in the book. They say, hey, if you want the proof of this theorem, go take analysis in a couple years. All right? However, we are very much in a position to understand the intermediate value theorem. Okay? So here's what it says. Actually, I have it written here on the slide for you. Boom. Suppose f of x is what? That's why it's in this section. Because the only thing you really need is you need to have a continuous function. Do you guys know what I mean by a closed interval? What's that mean? It has to include the endpoints, right? So this is continuous everywhere on the closed interval a and b. Okay. So here's the little experiment that we're going to do here in a moment. On your paper somewhere, actually, I'm going to cover this up so you can't possibly copy the rest of it yet. Oh, man. I'll put it back in a second. But here's what I want you to do. I want you to draw a little graph. And on the x-axis, I want to put a closed interval, a, b. So we're going to include those endpoints. Okay? And somewhere up here, let's start drawing my function. So this will be the point. I guess this will be f of a. Okay. So that's the point a f of a, right? And somewhere up here, let's put the point b, and so this will be f of b. Okay? So you're going to do two things here. Number one, I'd like each of you to draw a continuous function connecting those points. Well, continuous. That means don't pick up your pencil. We're going to obviously have different functions, aren't we? And then step two is when I put back the words of the theorem. You can finish copying it down if you want. But on your picture, I want you to put k in the correct place. And that's a very important observation. So I'm going to give you guys a little time to do that and talk to each other about what you're doing. Go ahead. Well, so k, it says, is between f of a and f of b. So which axis does k have to be on? Has to be on the y-axis, right? That's important to understand. So you can put anywhere you want, but I'm going to put k somewhere between f of a and f of b. It could be directly between, I don't know, somewhere in between. And then you guys did all draw a continuous function here? So I'll draw one. I guess I'll draw something that looks kind of like a parabola. I don't know. But you could draw a trig kind of function. There's a lot of functions. You could draw a straight line, right? There's a lot of ways to get a continuous function. Okay, now, The word is intermediate value theorem. You see, K is your intermediate value. Does that make sense, the words to you guys? Because K is between f of A and f of B. It's an intermediate value. Well, this theorem is an example of what's called an existence theorem. Something exists. I'm going to let you talk to each other and say, hey, because we have a continuous function, what is the rest of the theorem going to say? Because right now, this is only half the theorem. This is the suppose. The conclusion is about to be, there exists... Well, we'll let it go. Talk to each other for a minute, see what you come up with. Here it is, guys. I used my backwards E for there exists, just for case. No, it's a shorthand. Then there exists, what's that say? Some number, C. Where does C live? Well, somewhere on the closed interval AB. So it might even be that C equals A, or B, or something in between. Such that is what that colon means. That's really taking it shorthand here. Such that what happens? F of C equals K. I'm going to show you where my C is. Wait a minute. There exists C on the closed interval AB such that, what did we say it was? F of C equals what? K. All right, so I need F of C to equal K. Okay, there's K. Ah, there it is. Right there. If I take this to be my C, right there, won't it be true that F of C equals K? And I'm telling you that's actually a very hard theorem to prove. But I'm also telling you it's a very important theorem. And the only thing we really assumed about F is that it's what? Continuous. Is it important that F is a continuous function? Yes. Let me show you why. Classic example of a function that's not continuous. Let me show you this over on the corner here. Here's a function that is not continuous. It's called a step function. I don't know if you've seen this before, but it kind of looks like this. Maybe you have, you know what this could be? Those of you that did the Chapter 1 review, there was a problem where they said, hey, you're going to pay $2 to park in the parking garage plus an extra 50 cents for each half hour. So $2, and then if you go another half hour, it's $2.50, right? It's not a continuous function. If you go for 15 minutes, you won't have to pay $2.25. You guys with me on this? If I had this kind of function, would the intermediate value theorem work anymore? No, it has to be continuous. But the proof theorem is very challenging, so we're going to stay away from it. But we're going to use the theorem. As a matter of fact, let's use the theorem now. Well, actually, before we do that, why don't you take just a minute to find C on your picture. That's worth doing. On the group work, I said, show that there is a number x, right? That's existence. Such, between 0 and pi over 2, such that x equals cosine x. Let me draw a picture, guys. And the way to do this theorem is to use the intermediate value theorem. So watch how this goes. I'm going to let my function f of x be the function x minus cosine x. I'm going to let that happen. You might say, why'd you do that? Well, I've done this before. I know that this is a good idea. Because if I want to show that someplace x equals cosine x, by the way, do any of you know how to solve that equation? Me neither. Okay? But, is there a solution? We're about to see yes, there is. And basically what I need to do is we need to show f of x equals 0 for some value of x. Does that make sense to people? If I show that this equals 0, then x will equal cosine x at that particular place. Who's with me? Who is lost? Okay, start again, Paul. Is if we compute a couple of values here, guys. What is f of 0? Well, that's easy. It's 0 minus the cosine of 0. What's the cosine of 0? 1. So this is 0 minus 1, so it equals what? Okay, so f of 0 is negative 1. That's my f of 0, right? What does f of pi over 2 equal? Well, that's pi over 2 minus the cosine of pi over 2. What's the cosine of pi over 2? Cosine of pi over 2 is? 0. This is pi minus 0, so it's just pi. That's f of pi over 2 minus 0, so it's just pi over 2. That's what f of pi over 2 is. Okay? So f of 0 is negative 1. F of pi over 2 is pi over 2. And I'm going to say one more thing. Let k equal 0. Notice that f of 0 is less than k, and that's less than f of pi over 2. Right? This is the a and the b. The a is going to be 0, and the b is going to be pi over 2. And we're going to show that somewhere on there, the value goes somewhere between negative 1 and pi over 2. Somewhere it has to equal 0. We've got it. Oh, we almost have it. For the intermediate value theorem to work, you need to know one more thing. Do we have that? Do we know that f of x is continuous? I'd like to say that. Can I say that? F of x is continuous. How do I know? It is the word, I guess, is difference. What does that mean? The difference we subtracted two continuous functions. Okay? By the mean value theorem, I'm sorry, by the intermediate, I almost screwed it up, value theorem, there exists a value c such that f of c equals k, which is 0. And we're done. Because if we get f of x to equal 0 somewhere, then we have x equaling cosine x also. Do you understand? I think I'll start when I do 29 here. I just want to start and make sure that we have a good definition for what this means. It says limit as x approaches, is that 4? Okay. So if you want to do this problem, you need